So we'll start our discussion today. The topic is state, general action, MDP. Okay, so this is somewhat of a technical topic because now we are no longer in the finite state, finite action setting. I think the finite state, finite action MDP has been studied quite extensively in the past 50 or so years. A lot of results have come up in this particular area, and we have discussed many of those results in the previous lectures. But I think the future sort of belongs to general state MDPs, and the reason being that many of the newer, more modern applications of reinforcement learning are happening in the general state setting. So to give you an example, some companies / some people, researchers, they are trying to figure out if reinforcement learning can be used to design drugs for cancer or for any ailment. And the idea is that if you look at a molecule, if you look at a drug molecule, it's basically a bunch of atoms taking a specific form inside the human body. And it is that form, that structure, that allows that drug to interact with appropriate chemicals or appropriate bacteria or appropriate uh, uh, viruses in order to make them ineffective. Okay, and that's what the drug is supposed to do. So people are looking at how can we use reinforcement learning to figure out what molecule would make sense inside a human body for a specific disease. If you look at personalized healthcare, which is another area, the idea is if I look at your body history, if I look at your genomic history, what kind of genes you have, I could predict what kind of problems you will have in the future, as a result of which I can come up with specific drugs that would treat those problems in the future. The third kind of example is materials discovery. So let's say somebody comes and tells you that I want a metal that can withstand 1800 degrees Celsius temperature inside a turbine, and at the same time is easy to recycle or whatever, like some property, like it should have Young's modulus of X, or it should have heat transfer coefficient of Y and things like that. And once again, the idea of creating a material like that is you basically arrange a bunch of atoms in a 3D space and you try to understand what the material property of that particular uh, collection of atoms is going to look like. And so the way they do it is you are again using reinforcement learning, or at least some people are using reinforcement learning to do that. I don't know much about that particular area, but what they tend to do is they pick a set of atoms in a specific proportion, and then they do some molecular dynamic simulation on the set of atoms, and it tells them exactly how the atoms are going to move if certain stress is applied, if heat is applied, and so on. And then that gives them a reward, which is whether this is meeting the requirement or not meeting the requirement. And if the reward is low, then they need to figure out how to change the proportion or change the structure of how the atoms are placed in order to change the material properties of that new material. So in general, I think the general state MDP and robotics is another application. So how many of you know about this vision language action models, VLAs? Few people, right? So VLAs is the latest craze in Bay Area. And the idea is that you can give a command to a robot and the robot will convert it into specific motor commands that they can then execute on the robot in order to carry out a task like folding a cloth or cleaning up the table. And so there also, if you look at the robotic manipulators, these are all continuous state, continuous action objects. And therefore, again, general state MDP would be very useful for studying problems of those type. And I personally have been working on general state, general action MDPs for quite some time. And so I'm very happy to share some of my own insights on this topic. So now we'll make a small change in the notation. So S is the state space. A is the action space. So I want to change the notation because earlier we were looking at discrete state, discrete action. So one of the properties of discrete states, I mean, what is a discrete state? So the distance between any two points, distinct points, is equal to 1. That's a discrete state. When we look at a general state setting, now you have a notion of distance and you have a notion of ordering. Okay, so that's how I distinguish between discrete and general. So general will have a metric in the state and action setting, and it will have some sort of ordering. It may or may not have ordering, but it could have some ordering, which is the usual ordering partial ordering we can consider on Rn Euclidean space. So we'll talk a little bit about ordering in the future. But the way you differentiate or distinguish between finite state and general state setting is, in finite state, the distance between any 2 points is equal to 1. And in the general state, there is a notion of near and far, and there is a notion of bigger and smaller. Okay, so those two notions, as soon as you have those notions, you are no longer in a finite state setting, you are in a general state setting. Okay, then we have AS, which is the set of admissible actions at state S. Generally speaking, in the context of robotics and in the context of control systems, typically A of S would be written as A in A such that G of SA is less than equal to 0. Right? So I'm sure you have seen inequalities of this type in your optimization class or in some sort of constrained optimization class. So, so these are typical constraints that people consider in robotics or in autonomous driving or energy systems kind of applications. We have mu, which is a policy that maps the state to probability distributions over actions or state to actions such that support of mu of S is a subset of A of S. Or mu of S is in A of S. And I'm going to define the graph of A SA such that S is in S, A is in AS. That's graph of A. And we have cost function. C is graph of A to 0 infinity. This is cost function. Once again, if you have a reward function multiplied by a negative, scale it up a little bit in order to make it a cost function. And then transition kernel, which is graph of A to probability distribution over the next stage. This is the transition kernel. Typical examples of transition kernels. S prime equals to, maybe I'll use capital F, or S prime equals to capital F SA plus W. W is the noise. So some papers would say W is an actuation noise, some papers would say it's a noise, and some papers would use the transition kernel. Okay, so It depends on which paper you are reading. You could be in one of these three settings. Okay, so let me show you what graph of A typically would look like. So this is my state space, this is my action space, and let's say I have so this is S, this is another S prime. These are all the actions that you can pick. So no matter which state you pick, say you pick S tilde, these are the actions, the set of actions you can pick at S tilde. Okay, so this is how the graph of, so this set is known as graph of A. Yes?
So we're still in discrete time?
We are still in discrete time.
Okay.
Yeah.
So because I notice you're using S prime instead of like a time index. I think S prime must be the new state, right?
S prime is the new state, yeah.
So is there a reason we're not saying like S at t plus 1 equals F?
We can say it that way also, but remember in the transition kernel we typically say ds prime given SA. So we can say st plus 1, st at wt. That's fine. Yeah. So no matter what state you pick, there is a set of actions that are admissible, and you can only take actions within this. If you're using a randomized policy, Markov randomized policy, then the support of the distribution of the policy at S must be inside this admissible set. So maybe you are randomizing between action here, and action here. Alternatively, if you are in a deterministic policy setting, then your mu of S must be in the set A of S. Okay. Yes.
Sorry, I'm trying to understand the horizontal axis. So S prime is this S prime different than your old S prime? Is that the new?
No, this is this is a different S prime. So I want to show. So on a real axis, the state. So this is your state space.
In that interval.
Yeah, the state is in that interval.
Okay, and then the action.
And the action could be
state dependent.
Yeah, so but it is state dependent, so only these are admissible actions. So this is graph of A. Okay. And so if you look at the cost function and the transition kernel, they are functions of graph of A. So the cost is only defined here, the cost is not defined here, the cost is not defined here. Same thing with transition kernel, it's defined here, but it's not defined here and here. Because those actions are, this action is not feasible, this action is not feasible, so there's no point defining a transition kernel or a cost function in those areas. Typically speaking, if you look at papers in the computer science community, typically they don't really have state dependent action sets, so there's no notion of a set of admissible actions. But if you look at control theory or robotics sort of area, then there is a notion of a set of admissible actions. So something to keep in mind. Some papers may not be considering it, some paper may consider it. Any other question? Yes.
Can I ask
yes.
General question?
Yes,
so
of course.
What's the advantage of considering this general state and general action theory instead of we still considering finite MDP, but with some function approximator errors? Because we are using
Right. Very good question. So it'll become clear in a little bit, but basically what happens is when you're using a function approximator, you're implicitly imposing a Lipschitz continuity requirement from state to action or from from, if you are using reward function or value function, you are requiring the value function to be Lipschitz. If you're using neural network, for instance, Lipschitz implicitly means that now there is a metric on the state space, right? So if you're not very careful, if you pick, so one thing that we will, when we talk about the function approximation theorems, and when we talk about Lipschitz MDP, which will be in probably next class, it'll become clear why, when you're using function approximators, why exactly those problems seems to converge to a solution. And it's because there is an underlying structure, metric structure on the state space, because of which you are able to converge. And in cases where you don't converge, it's because that metric structure is not there, and your function approximating class is very small, as a result of which you're not able to approximate the value functions or the policies very well. So, so all of this is interconnected in the sense that, remember when in the lecture 1 we were talking about, you have observation, you have action that influences the next observation, then you come up with the state space. Now you can come up with discrete state space setting as well, but if you are using function approximation, then implicitly you are saying that there is a metric structure on the state space, because if I'm using function approximation and those function approximators are Lipschitz, which is the case in neural network and deep reinforcement learning and transformer based models and so on and so forth, you are imposing the Lipschitz structure by the virtue of using a specific function approximating class, and you're not being explicit about it. So I want to make it very explicit that, look, we are in a general state setting, there is a metric structure on the state space, I'm using a Lipschitz function approximating class, and that's why my algorithm is working. And if you don't make that case, you are just not being clear about what you are trying to solve. Okay? Yeah.
When you talked earlier about the metric and the ordering,
Yes.
is the ordering on the metric?
No, ordering is typically independent of metric. So in the case of real line Rn, remember we say that x is less than equal to y, where element wise each element is lower than y element of y. So that's an ordering. That's a partial order on the space of Rn. And you can define it on the space of Nn and on the space of Zn as well. You can define these orderings, but it has nothing to do with the metric. You can pick whatever metric you want on the space. Any other question? Okay. So as is the case, we have alpha, which is the discount factor. Okay, so typical examples. So you could have, generally speaking, this WT in the context of, say, Kroger, if ST is the inventory, AT is the fulfillment, WT would be the demand, that people are coming and buying X gallons of milk and Y pound of cheese. That's typically this WT. There are very few cases where you have a transition kernel, but you don't have an explicit noise. It can happen, technically speaking, but generally speaking, these models are good enough for most problems. But sometimes, at least in all the papers that you will read, they'll always start with this kind of structure where there is a transition kernel. But whenever you see a transition kernel and you're not very happy with this sort of notation, you can just implicitly assume that there is a noise process that is driving the state of the system. Okay, so there is a discount factor alpha. As is the case, we have the objective function, let me call this J mu, which is a function of the initial state S naught. Let me write it as S, expected value of summation t equals 0 to infinity alpha raised to t C of STAT given S naught equals to S, and AT AT is generated from the policy mu. So either AT equals to mu of ST or AT is distributed according to mu given ST, depending on randomized or deterministic policy. Now, when you are in this general setting, things become a bit complicated. So I have to introduce all that complications in today's class. So the cost function could go all the way to infinity. So it's not very clear if this summation is going to converge. So when we were in the finite state setting, the cost was always bounded. Okay, so we didn't have to worry about this expectation not being defined. The other issue was, so it's not very, so of course we want to, the goal is to compute mu star, which is argmin of mu of j mu s. So starting from the state S, if I'm picking the action, if I pick the policy mu, what's the minimum, what's the best policy that I can get? And then the question becomes of existence, whether such a minimum would exist or not exist. So a lot of the work in the past 50 or so years have been done, largely in mathematics community. I mean, I would call it a mathematics community because those papers and books are very abstract. In order to prove that this argument is well defined and that there is a v mu star, which is j of mu star of s. So there is a value function of the optimal policy corresponding to the optimal policy, which is given by this particular expression. So what I'm going to do today, I'm going to give you two different sufficient conditions on this thing so that this is well defined and the minimum exists. Okay, so that's what I'll be doing today. Yes.
How important is it to have this unbounded cost? Like, I understand.
So linear quadratic has unbounded cost. Yeah. But I think from an applications viewpoint, it doesn't matter. We never are in a situation where the cost is unbounded because there is always something saturating within the system, and that saturation, something will explode, something will happen, after which the cost is never going to get accrued. But I think from a mathematical perspective, a lot of people who have done this general state MDP setting, they are mostly mathematicians, and they care about all kinds of general problem statements that could appear, and that's the theory. Like those are the books that have been written on this particular topic. So the most important example being linear quadratic tracking problem. So we have an unbounded cost in those settings, but practically speaking, will never be in that unbounded region. Any other question? Okay. Wonderful. How many of you have heard of this compact set? How many know about compact sets? Few people? Okay. So let's talk a bit about a few important results. So I'm going to assume that the state space is a metric space. I'm going to assume that the action space is also a metric space. For those of you who are not very familiar with real analysis related results, and I'm kind of assuming that most of you have not taken a course in real analysis, just assume that the state space is a subset of Rn1 cross Nn2 cross Zn3. And same thing, action space is also a subset of a similar thing. And you can put some metrics. you can define some metric on this space. So if you are in Rn, you can have LP metric, LP metric, L2 metric or whatever. Same thing with N, same thing with Z. So you can define whatever metric you want that makes sense for your specific problem. Okay. So your state space is a subset of this, and action space is a subset of some space like that. Some of the problems that we have studied within our group, we had situations where N1 is of the order of 100 to 500, and this N2 is of the order of 100 to 500. Okay, but we never worked in situations where I had an integer variable, but I'm assuming some of you might have that situation in your research. Yes.
So when you put those X's, to me that means like the state space is that triple. Is that what you mean? Like you have R1
Rn cross N cross Z. So you could have
state has like a real component,
an integer component, and a natural number.
Is that always the case?
No, it depends on situation. So
this is like this is one
example. Yeah, one possibility where N2 could be 0 and N3 could be 0. Okay. Or if you are in an inventory setting, then N1 would be 0 and you will have only N2 but no N3, so N3 would be 0. So you could have situations that are very general. Any other question? Okay. So let me start with the compact set. So if this is your state space, so in finite dimensional spaces, K is a subset of S cross A is compact. So S cross A is finite dimensional. Then K as a subset of S cross A is compact if and only if it is closed and bounded. So in a finite dimensional setting, when you have Rn1 cross Nn2 cross Zn3, so that's a finite dimensional space. The dimension is N1 plus N2 plus N3, so that's a finite dimensional space. A set is compact if and only if it is closed and bounded. Boundedness is always a function of the metric that you have picked, right? And closeness is also a function of metric, because you want to show that every sequence that converges, the limit point is in the set itself. Okay, so that's compact. So whenever I mention compact in the future, just implicitly assume, if you are thinking of finite dimensional spaces, just implicitly assume that it is closed and bounded. If you are in general metric spaces, that's not the case, but in finite dimensional cases, that is indeed the case. Then I want to talk about lower semi-continuous functions. How many of you have heard this term lower semi-continuous functions? Few people. So what are lower semi-continuous functions? So imagine you have a discontinuous function. Okay, so at the point of discontinuity, so I have a function f of x. This is my x, and I have a function like this. So I have this point of discontinuity. There is a point of discontinuity here. Let's call it x tilde. So at x tilde, the function is discontinuous. What's the value that the function should be taking? Okay, so let's assume that the function takes the lower value at the point of discontinuity. It's a lower semi-continuous function. If the function takes this value at the point of discontinuity, it is an upper semi-continuous function. And if the function takes a value which is in between, it's a discontinuous function. It's neither lower semi-continuous nor upper semi-continuous. Okay, so so function f is lower semi-continuous if at the point of discontinuity it's taking the lower value. How do we write it mathematically? So I'm going to use this set X. So sometimes X could be the state space, sometimes X could be the action space, and sometimes X could be the state cross action space. So I'm using X as a placeholder for any space. Fx to R bounded from below is lower semi-continuous. I'm going to use LSC. LSC, lower semi-continuous, is LSC if and only if for every x in capital X, for every sequence xn such that xn is converging to x, lim n goes to infinity, f of xn is greater than equal to f of x. So I have a function which is bounded from below. This is a function bounded from below. And at every point x, so in this case it's continuous everywhere except at this particular point. And at the point of discontinuity, no matter what sequence I pick, the function value at x is less than the limit of the function value at xn. Okay, so if I pick a sequence here, the limit is going to be here, but the function value at x is lower than the function value at the limit. So lim n of fxn is greater than or equal to f of x. Okay, that's a lower semi-continuous function. So we have all heard about continuous functions. This is the first time I'm assuming many of you are seeing lower semi-continuous function. So lower semi-continuous functions are allowed to be discontinuous as long as the function value at the points of discontinuity is a lower value of the two values. Okay. Any questions on the lower semi-continuous function? No? Let me write down the properties. F1, F2, LSC, alpha 1, alpha 2 greater than or equal to 0, then alpha 1, F1 plus alpha 2, F2 is also LSC. Level sets x in x such that f of x is less than or equal to lambda. This is called a level set, is closed for all lambda. So if f is lower semi-continuous, then the level sets of the function f is closed for all lambda in R. Okay, so I have two important properties. There are many important properties of lower semi-continuous function, but these one would be important in our discussion. So if I have two lower semi-continuous function, I add them up with positive or non-negative coefficients. The new function is also going to be lower semi-continuous. If you multiply a lower semi-continuous function with a negative value, then it becomes upper semi-continuous, which is something we don't care about right now. The second thing is, if you look at the level sets of a lower semi-continuous function, it's always going to be closed. It's going to be a closed set. So let's look at an example. Maybe I'll erase this side. So I have a function f of x. This is x. Okay, so the function is taking the lower value. This is a lower semi-continuous function. Let's consider a value lambda. What's the set of x at which the function is below lambda? So that's this part and then this part. Is it a closed set? It's a closed set, right? So that's what the second property of lower semi-continuous function is saying. And you can move this lambda up and down, and you will always have that situation where you will always get a closed set. Okay, and of course, if you put lambda way below, then you will have an empty set, but empty set is by definition both open and closed. So, okay. Any questions on the lower semi-continuous functions? Yes, please. Yes, so we are looking at the level sets of f. Okay, so how is the level set defined? So I pick a lambda value and I cut the function and I look at where the function is below lambda, at what values of x is the function below lambda. So that's this part, and this point is included and this point is included, right? Because the function value is here, not here. So this point is also included. So this is a closed set, and that's what we mean by LSC. Okay. The second class of definition I want to talk about is inf compact. Inf compact. I have a function from x to r is inf compact if the level sets of f x in x such that f of x is less than or equal to lambda is compact for all lambda in R. That's the definition of an inf compact function. Remember, compact means closed and bounded in the finite dimensional setting. So if X was a finite dimensional space, you want this set to be not just closed, but you also want it to be bounded. Let's look at another example. E raised to x, this is R. It looks something like this. Let's look at a level set. What is the level set of e raised to x? So what's the set of x in R such that e raised to x is less than equal to lambda? This is minus infinity and log of lambda. Is this a closed set? Okay, half the class is yes, half the class is no. Okay, so remember minus infinity is not included. Okay, so this is actually a closed set because it's an interval. It's a closed interval. Okay, so minus infinity is never included in real line. So it's a closed interval, as a result of which this is a closed set. Is it a compact set? Is it a bounded set? It's not a bounded set. Okay, because it goes all the way to negative infinity. So if you draw a ball of radius r, no matter how big of an r you pick, you cannot contain this entire set within that particular ball. So it's a closed set, closed but not bounded. So this is not inf compact. So e raised to x is not inf compact. E raised to x is LSC but not inf compact. Okay, so it's a lower, so e raised to x exponential function is a lower semi-continuous function over the space of real line, but it's not inf compact because the level sets are not compact. Let's look at another function.
But there's no discontinuity.
There's no discontinuity here. So continuous functions are always lower semi-continuous. It's when the functions become discontinuous, then complications arise. Let's look at another function. This is x square. This is x. Let's look at a level set. Is this a closed and bounded set? Right? So I can draw a ball of radius r and I can contain this entire set by picking a ball appropriately large. And it's a closed set because these endpoints are included, as a result of which it's an inf compact. So x square is inf compact. So f is inf compact here because the level sets are closed and bounded. In the general metric space setting, you want the level sets to be compact. Any questions so far?
So does the impact is equivalent to the coercive?
I have not seen the comparison between the definitions of inf compact and coercive functions, but it seems to me that coercive function should be inf compact.
Okay.
So it should go one way, but I don't know whether it goes the other way or not. Okay. So by looking at these two pictures, this picture and this picture, what can you say about the minimum of functions that are inf compact? Does the minimum of e raised to x exist? No, it doesn't exist, right? Because it goes all the way to 0, so it's always above 0, but it never goes to 0 because it goes to 0 at minus infinity. It's not part of real line, so it doesn't have a minimum. But if you look at an inf compact function, you will always find a minimum. Okay. Remember, we are trying to minimize discounted cost setting. So if you have inf compact cost, you will always be able to find a minimum. If you don't have inf compact cost, we don't know whether a minimum would exist or not exist. Okay. So I want to talk about the third result, which is, so this is definition. I want to talk about a result which is called Weierstrass extreme value theorem. How many of you know about Weierstrass extreme value theorem? No? Okay, few people. Let's talk about that. So I have a function which is a lower semi-continuous function. X is compact. Then there exists x star such that f of x star equals to nth x in capital X f of x. So if I have a lower semi-continuous function and I'm looking at the lower semi-continuous function over a compact set and I want to find a minimum, there is always a point x star which achieves the infimum. So therefore there is a minimum. So the minimum exists. When we were in a finite state setting, finite state, finite action setting, this set X was always finite. Okay, and we never have to worry about existence of a minimum because all functions are continuous over a finite space and all sets are compact over a finite space. Okay, so we didn't have to worry about it. Now we are in a continuous state, continuous action setting. So we need to worry about compactness. We need to worry about lower semi-continuity. And this result comes to our rescue because a lower semi-continuous function over a compact set achieves the minimum. Yes.
Back on this, is this for lower semi-continuous only, or just for?
So inf compact will always be lower semi-continuous because a compact set by definition is closed, and the level sets are by definition closed here. So that's another result, which is f is inf compact implies f is LSC because the sublevel sets are closed. Any other question? So whenever we are in a continuous state setting, we don't want to be minimizing functions that are like e raised to x. We want to be minimizing functions that are like x square. Okay, that's how you should think about. Or alternatively, your state space is compact, and your function f is lower semi-continuous, and your state space and action spaces are compact. Okay, so now we are yes.
Sorry, so before when you were talking about impact, you said that the main reason you're talking about it is because the minima exists.
Yes, the minimum exists in compact. Yeah.
Is that separate from the extreme value theorem, or is the extreme value theorem different?
So great question. So if your sublevel sets are compact in an inf compact function, if your sublevel sets are compact, then you can always find the minimum within the sublevel set, within one sublevel set, just pick whatever. And that's the minimum of that particular function, right? So even if my function is highly non-convex, let me draw a highly non-convex function. Something like this. I pick the sublevel set lambda. So what all sets do I have? I have this, I have this, I have this. That's it, right? So I have 3 disjoint subsets. That's the sublevel set. It's a compact set because it's closed and bounded, and the minimum is achieved at this particular point.
So the extreme value theorem is like separate.
It's separate from the inf compact. Inf compact is more general.
Okay.
Yeah, inf compact is more general than extreme value theorem for sure. So extreme value theorem requires this set X to be compact, What happens in inf compact function is you can always ignore the function that is above a certain bound because you know that the minimum doesn't exist there. Now you can just focus on a compact set and you can find the minimum within that compact set. Any other question? Okay, wonderful. So we understood some of these. So what all things have we done so far? We have done lower semi-continuous functions. We have done inf compact functions. We've talked about extreme value theorem. Now we will talk about strongly continuous and weakly continuous transition kernel. Okay, so that's a bit complicated. So I'll go very slow for this particular part. So I have two spaces, general spaces, x, y. These are two metric space. I have a transition kernel, or let me not call it transition, I'll call it a stochastic kernel. Phi of dy given x. So phi maps x to probability distributions over y. I want to look at the following functions. So I pick a function f of y. I take the integral phi dy of x, and I want to look at this function as a function of x. Okay, so in the context of MDPs, okay, I'll let you guys write. Okay, so in the context of MDP, this x would be the state action pair, this phi would be the transition kernel P, and this would be the next state. Okay.
What you say is the dy is the small interval of the v of the y.
Yes. So phi of dy given x is the same as phi of y plus dy given x. So you look at a small infinitesimal interval, and whatever is the probability measure over this infinitesimal interval, that's given by phi dy given x. Okay, so I have two metric spaces x and y. I have a stochastic kernel that takes as input x, gives me a probability distribution over y. I'm going to take that transition, the stochastic kernel, and I'm going to average out a function f. Now this becomes a function of, this whole integral becomes a function of x. And now I want to know what the continuity property of this particular function looks like. This function of x looks like.
Can I ask you a question?
Yes, please.
What is the meaning of f? Is it probability of y, probability distribution of f or y?
What does this mean?
Fy, what is fy?
No, fy is a function. F is a function from y to r.
Is it a PDF?
No, it's just a function of y.
Oh, okay.
So it could be a cost function, for
Oh,
instance, right? It could be any function. So we could pick continuous functions of y. We could pick discontinuous functions of y, right? We could pick bounded functions of y. We could pick unbounded functions of y. So depending on what class of functions you are picking, this particular mapping will have different properties. Okay, so there are two definitions. So phi is strongly continuous So this is called strongly continuous if and only if x maps to integral of fy phi dy given x is continuous in x for every function f from y to r that are bounded and measurable. I know we haven't talked about measurable functions. I think we talked about measurable sets long time ago at the very beginning of the class in lecture 1. But whenever I write measurable functions, think of them as continuous functions and all well-behaved discontinuous functions. Okay, so the function f has to be bounded. So we are not looking at unbounded functions, and we are looking at well-behaved discontinuous functions and continuous functions. Then phi is called strongly continuous. I'll give you an example. So y equals to f of x plus w. F is continuous x is Rn, y is Rm, w and then w is Rm, and the noise w has continuous density function nw. So far we talked about functions. Now we'll talk about the transition kernel, because those are the two important things in MDP setting. So yes, yep.
In your example, what is the smaller f?
This function?
Yes, what is it?
So this can be any arbitrary function that is bounded and measurable.
Oh.
Arbitrary.
Oh, I see.
Okay. So let's evaluate this integral for this particular setting. So we have this as the example. So what is integral of fy phi dy given x? This is integral of fx plus w nw dw. So wherever I have y, this is the same as expected value of f of y given x. So I replace this function with f of x plus w times the density function of w times dw. I can do a change of variable. and I can call it f of y n of y minus f of x dy. That's change of variables. This is continuous, and this is continuous and bounded. So as a result of which, how many of you know bounded convergence theorem? I assume no, not many. Okay. So so there is something called bounded convergence theorem, as a result of which this function is a. So remember, this integral we are averaging y. It's only a function of x. This function f is continuous. This function n is continuous. As a result of which, this entire integral would be continuous function of x by bounded convergence theorem. Okay. This material is taken from the book. It's a hard to read book, but the book's name is, book's authors are Hernandez, Lerma. This is 1996. Okay, so if you look at the appendix of that book, you will be able to find all of the stuff that I'm talking about. So all of the stuff is taken from there. However, I would caution that the book implicitly assumes that you have a background in real analysis. So if you don't have the background, you probably will not be able to understand much of the appendix. So I'm cherry picking important results from there, and I'm writing it here because it makes it easier to understand. Yeah.
I still have a question.
Yes, go ahead, please.
For the first step of your derivation, why does the phi function disappear?
This function.
Yeah. Well,
So phi is the stochastic kernel that is induced by this particular function, this particular map. Okay. So this one is same as computing expected value of f of y given x. Okay, it's the same thing. I'm rewriting the same thing in the format that you probably already are familiar with. And then all I'm doing is replacing y with f of x plus w, and then doing a change of variable in order to show that this is a continuous function of x. Any other question? Okay. So this is strongly continuous. The reason why it's called strongly continuous is because I'm assuming that these functions are discontinuous. It becomes weakly continuous so the next definition is phi is weakly continuous if and only if x maps to integral of fy phi dy given x is continuous in x for all continuous functions, continuous and bounded functions f from y to r. Okay, so this is known as weakly continuous because now I'm removing all the discontinuous functions from the test functions here. Okay, so it's only continuous and bounded functions that I'm using here, whereas here I'm using strongly continuous because I have discontinuous functions as well. So let me give you an example. Y equals to f of xw. F is continuous. Implies that phi dy given x is weakly continuous. Okay, so in this case, I needed to have an additive noise with a continuous density to make it strongly continuous. In this case, I don't need to make any assumptions on the distribution of the noise. As long as this function that's mapping x and noise to y, if the function is continuous, then phi becomes weakly continuous. Okay. I don't expect you to understand the proofs of these things because it requires a background in real analysis. But those of you who might take real analysis in the future, you can go back to the book and you can read all of this stuff and understand what the authors are trying to say. Okay. So now we have all the ingredients that are needed in order to prove under what conditions the MDP will have an optimal solution. Okay, so let me write down two general. Okay, I'll wait here for questions. Any questions so far? Yes.
So we could also, this expectation, we could write that as expected value of f of phi of x.
This one?
Just the so like for that y inside the expectation,
Yes.
we could plug in phi of x as another way of understanding this. Because phi takes x and gives out a random variable.
Right. So let's say let's consider this particular setting. So my phi of dy given x is Dirac function of y equals to fx plus w dy. So Dirac function gives you the entire weight on f of x plus w and gives zero weight to all the y's that are not f of x plus w. So this is the stochastic kernel, and I'm not sure if what you mean by replacing y with phi. Do you mean, what was your question? Sorry, I forgot.
I guess I'm just trying to understand how it all fits
Uh-huh.
together. So because here there's an implicit relationship between y and x that's
Yes.
defined by phi.
That's defined, yeah, exactly. So this is how you go from a explicit equation to a stochastic kernel from x to y.
I guess I'm just trying to, like, if we had one expression and we were trying to fill in what's missing there, you could say, like, after the x, you could write comma, y is distributed according to phi of x.
Yeah, that's
Just to,
that's right. Y is distributed according to this. Yeah. Right. Okay. Any other question? Okay, wonderful. So let me write down the main results. These results are, so if you read the classical books, you won't find these results, but the results comes from somewhat newer papers. So let me give you two specific results. So this is Feinberg and Lewis, 2007. So C cost function C graph of A to 0 infinity is inf compact. So what that means is C of S A less than equal to lambda is compact for every lambda in R. And the second requirement is the transition kernel P is weakly continuous in SA for all SA. This implies mu star exists. So this is a book, Hernandez, Lerma, and Lecere. It's a very famous book in discrete time Markov decision processes. So here the requirement is the first C from graph A to 0 infinity is LSC. And CS is inf compact over A for all S in S, and the second is P is strongly continuous in SA for all SA in graph of A. And the third requirement is there exists a policy mu such that J mu x is less than infinity for all S in capital S. Okay, so this is a sort of a classical result. The cost is non-negative, lower semi-continuous, CS. So for every S, if you look at CS as a function of A, it's an inf compact function over A, and this is true for all S in S. The transition kernel is strongly continuous, and there is a policy which gives you a bounded cost no matter what state S you start from. Okay, so that was the classical result. This is the result that everybody in the general state Markov decision processes, this is the result that everybody understands very well. This is somewhat of a newer result and less cited result. This generalizes this requirement of strong continuity. So strongly continuous transition kernels are very complicated. Very few cases where you will have strongly continuous transition kernels. So this one requires weakly continuous transition kernels, but at the expense of having a cost function that satisfies a much stronger condition. You had a question?
Yeah, so should we remove the 3? Like 1 and 2 are conditions.
Yes.
And 3 is a result.
No. 3 is also a requirement. So this implies.
What is the statement then? What do we get from those 3?
There exists a policy mu that gives you a finite cost at every state.
That's the third condition.
That's the third condition. That's a requirement.
Okay, then what is the final statement?
The final statement is mu star exists. The final statement in both these cases is under what conditions mu star exists, which is the optimal policy. So you have 3 different conditions, 3 requirements here for mu star to exist. You have 2 requirements here for mu star to exist.
And then in the first case, you never mentioned anything about an objective. So don't we need to say something about an objective to get an optimal policy?
So the objective was given at the very beginning of class. So we wanted to J mu of S, yeah, the discounted cost. Yeah. Any other question? We don't really have time, so we have only 3 minutes. So are there any further questions on this? So remember that. So I think I'll tell you why. So why I feel that this particular requirement is very strong. So I have ST plus 1 equals to capital F of ST AT plus WT. So here the noise has to be additive and the noise has to have full support over the entire space. Now, of course, you can make the assumption, even if your noise is bounded, you can make the assumption the noise is Gaussian and your life is good. But then you are actually making a much stronger assumption than what the noise actually satisfies. So this leads to strong continuity. Strongly continuous transition kernel P. On the other hand, if I assume ST plus 1 equals to F of ST AT WT and F is continuous function, all I have to assume is this function F is continuous function, then in that case, my P is weakly continuous, but I still get the existence of the optimal policy, but the cost function now requires to be inf compact. You want the cost function to be inf compact. So that's the trade-off you are making. Generally speaking, if you're solving a real-world problem, your cost function will generally be inf compact, and your transition kernel will generally be weakly continuous. There are rare situations where you will not have that condition satisfied, so this condition would be satisfied, but now your transition structure has to be much more stronger, and that makes it problematic. Another reason why this becomes problematic is if you have a deterministic system. So I have a robotic system, everything is very well calibrated, it's a deterministic system. If I give the motor a command, move 10 radians, the motor is going to move 10 radians. There's no uncertainty about it. So there's no notion of noise in that case. You no longer have strongly continuous MDP. You have actually weakly continuous MDP, right? Where the noise is not there, there's no noise. So that's why I feel that weakly continuous is a better assumption, because that encompasses all the deterministic systems that we have all studied from ECE 3050, 3551, 5551, and so on. So this one includes deterministic system. This one excludes all deterministic transitions. You cannot have any deterministic transition because deterministic transition will not lead to strong continuity of the transition kernel. Okay. So in the next class, I'm going to spend some time proving this particular result. It's instructive because it leads to the value iteration algorithm for MDP. So what we are going to do is define the value iteration algorithm for this, use all the results that we talked about in this class. So there are 4 steps of this proof. We'll only prove maybe step 2 and 3 because step 4 is far more difficult to prove, so we won't do that in the class. But the paper is here, so you can definitely read the proof from there. We'll do this. This one I'm not going to do the proof in the class, and then we'll talk about monotone value functions, and we'll talk about Lipschitz value functions. Okay, so that will be the next 2 topics. Thank you so much.